So that was a discussion of mainly of solids dissolved in liquids. What about gases in liquids? Gases dissolved in water. A can of soda is an example of a solution in which we have a gas, carbon dioxide, dissolved in water, which is a liquid. So gas in a liquid. And most liquids that are exposed to air or some other gas are going to have dissolved gases. Lake water and seawater contain dissolved gases, especially oxygen, and that's how the fish are able to survive, is the oxygen that's dissolved in the water. Your blood contains dissolved gases, nitrogen, oxygen, carbon dioxide, and one of its big functions is to carry oxygen to the tissues of your body and take the carbon dioxide away. And so you breathe out the carbon dioxide, you breathe in oxygen. Even tap water is going to have dissolved atmospheric gases. The solubility of gases in liquids does the opposite of solids. When you heat a liquid, the solubility of solids goes up. When you heat a liquid, the solubility of a gas goes down. And if we think about our experiences with soda, we can understand this. Here they're showing a cold bottle of soda being poured into a glass and a warm bottle of soda being poured into a glass. The warm soda is going to cause a lot more fizzing. You're going to lose a lot more of your carbon dioxide just when you pour it into the cup than if you do it with a cold one. And if you've ever tried making root beer floats, my kids are fans of root beer floats. If you try to make a root beer float with room temperature root beer, good luck. It fizzes all over the place as it hits that the ice cream. It's just so warm, and the carbon dioxide just comes out like crazy. You probably also know that if you have a cold glass of soda versus a warm glass of soda, the warm glass of soda will go flat much faster than the cold one. And that's another thing you could try at home. Put a glass of soda, just open glass of soda in the fridge, and a similar glass of soda just sitting on the counter. And wait a few hours and taste them and try them again the next day. And you should find that the one in the refrigerator keeps its fizz longer than the one that's out on the counter. If you want to get rid of the fizz in soda, just heat it up and all the fizz will come out. Here's another thing you can try at home. Put ordinary tap water in a pan on the stove and begin to heat it. And what you'll see as it starts to warm up is you'll start to see little tiny bubbles. And this has probably happened in lab this semester. You maybe just didn't notice it to pay attention to it. But you'll see these little tiny bubbles. And occasionally I'll have a student who's anxiously waiting for their beaker of water to boil come and ask me, "Is this boiling? I see bubbles." I'm like, "No, those little tiny bubbles." What that is the dissolved gases in the water coming out. Because as you heat the water, the solubility goes down. Less gas is soluble, and so that gas comes out of the water. So you'll see these bubbles coming, and then as the water gets to the boiling point, then you'll see big, vigorous bubbles coming. And that's actually the water vapor, not the dissolved air. The solubility of gases also depends on the pressure of the gas. And this is called Henry's law. The higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. So here we have two illustrations. So here are the gas molecules in one and in the other. This one has a higher pressure of gas. The higher pressure of gas, we can think of it as like forcing the gas into the water. There's an equilibrium here. And when we increase the pressure of the gas, we shift the equilibrium and we increase the solubility of the gas. When we decrease the pressure, decrease the concentration of gas molecules, the equilibrium shifts the other way. And we begin to lose our dissolved gases in here. And so this is what happens with a can or a bottle of soda. There's always a little bit of a headspace there. And when you open the can, you get that wonderful sound, right, of the carbon dioxide escaping. And you can see it when you open a bottle of soda. It's hard to see through a can unless you're Superman. When you open a bottle of soda, maybe it's orange soda, and it's just all orange, and you open the lid, and what do you immediately see? You start to see bubbles coming up, right? Where were those bubbles before? Well, the gas was soluble before because there's a high pressure of carbon dioxide at the top of that container. When you release that, the solubility decreases and the soda begins going flat. So there are some devices that you can stick on your 2-liter bottle of soda and pump a bunch of air in there, and people say, oh yeah, that'll make your soda last longer. Not significantly, because it needs to be carbon dioxide pressure, not just air. The percentage of carbon dioxide in air is pretty low, and so pumping it full of air is just not going to help much at all. It needs to be carbon dioxide pressure above the solution.